Last day before winter break, we began with this warm-up. What is the quantity of a plus b squared? The solution was not a squared plus b squared. The solution was to rewrite a plus b multiplied by itself. And then we have to use a distributive property, or in other words, FOIL. First times first is a times a. First times last, or outside times outside, is a times b. Inside times inside is another ab. And then last times last is b times b, or b squared. Our like terms are combined, and our answer is that a plus b, the quantity squared, is equal to a squared plus 2ab plus b squared. Then we spent 5 or 10 minutes with this picture, and we asked, what is represented by the quantity a plus b squared? So in this picture, a plus b is the length of this side, and it's the length of this side. So when you square a plus b and multiply it by itself, a plus b squared represents the area of the big square. Then I asked students to represent the area of this big square a different way. Remember, in part A, we represented it as side times side, or a plus b times a plus b, which we learned in the last slide was a squared plus 2ab plus b squared. But then I asked, can you represent the area a different way? So, what do you suppose students came up with? They said instead of thinking of the area as side times side, we could represent the same area as the pink plus the green, or 4 triangles plus the green square. And that would be the same area as side times side for the big square. So we played with that. The area of this whole square is side times side, and that should be equal to the representation of the area where we do that middle green square plus the 4 red or pink triangles. Well, we already worked this out. A plus b times a plus b is this quadratic trinomial. And the middle square is c squared, c by c. And then the area of the 4 triangles, well, each of those triangles area is 1/2 times base times height, where the base and the height are perpendicular to each other, which are a and b. So 4 times 1/2 a and b, which is 2ab. And then if we subtract 2ab from the left side and do it from the right side, we're left with a squared plus b squared equals c squared. And a lot of students recognize this immediately as Pythagorean theorem, which is the basis of this next lesson on section 5.7. Before we went into 5.7 on that class, we actually got our test back. And so I wanted to remind you that when you have parallel lines cut by a transversal, the alternate interior angle theorem says that the alternate interior angles will be congruent. The blacks and the greens, they're congruent. Notice that they are formed by the transversal and the parallel lines. So if the alternate interior angles are formed by parallel lines and a transversal, they will be congruent. So let's look at number 14 from our test. A lot of students thought that 2 and 3 would be congruent because of the alternate interior angle theorem. This is a proof on that test, chapter 4. However, in number 14, we did not know that the green sides were parallel. Since we don't know that the green segments are parallel, we don't know that these alternate interior angles 2 and 3 will be congruent. So people who said they were congruent by the alternate interior angle theorem were incorrect. However, angle 1 and 4 were formed by parallel lines because it was given that segment AB was parallel to CD. And since those alternate interior angles are formed by parallel lines, we can say that 1 and 4 are congruent by the alternate interior angle theorem. So that was a common mistake on that test, and we discussed it briefly in class. All right, let's move on to the lecture for the next section, 5.7. First of all, remember, we did cover section 5.1, but then we skipped 2, 3, and 4 and went straight to section 5.5. Here we are in this video talking about 5.7, which is the Pythagoras stuff. Pythagoras was a Greek mathematician, philosopher, who lived thousands of years ago, a couple of thousands of years ago, and while they weren't the first person to come up with this idea, they're the first person in recorded history, so the first person to get credit, and it's called Pythagorean's theorem. which says if it's a right triangle, then the square of the hypotenuse equals the sum of the squares of the legs. You're used to seeing a squared plus b squared equals c squared. I'm turning it around a little bit. I'm going to say c squared is equal to a squared plus b squared. Now, conceptually, if it's a right triangle, then the hypotenuse's square will equal the sum of the squares of the legs. C squared will equal a squared plus b squared. So geometrically, that means c times c, which is the area of the blue square, will equal the sum of the areas of the green and the red square. All right. If that's the Pythagorean theorem, and we proved it actually in the warm-up, then what's the converse of it? We would just switch the conclusion and hypothesis around. If the square of a side of a triangle is equal to the sum of the squares of the shorter two sides, then it must be a right triangle. So the converse is a way to show that a triangle is a right triangle. If the longest side squared is equal to the sum of the squares of the other two sides, it will be a right triangle. All right, then we talked about Pythagorean triples. So Pythagorean triple is the three side legs of a right triangle, but only if all the sides are whole numbers. So which one of these is not a Pythagorean triple? Well, they are all right triangles, but we had to find the missing side. So 5 squared equals 3 squared plus b squared, or x squared. Excuse me, we can do the algebra and find out that x is 4. All right, here we have the unknown side squared is equal to the sum of the squares of the sides 5 and 3. So the missing side is the square root of 34. And in this case, we have the hypotenuse squared is equal to the sum of the squares of the sides 7 and the unknown. And we can solve that and find out that the unknown side was 24. So these three sides are 7, 24, and 25. These three sides are 3, 5, and the square root of 34. And these three sides are 3, 4, and 5. They are all right triangles, but the only Pythagorean triples are 3, 4, and 5, and 7, 24, and 25. Because to be a Pythagorean triple, all the sides have to be whole numbers. And the last idea of this section are the Pythagorean inequalities. We already know the middle one. If the square of the longest side is equal to the sum of the squares of the other two sides, it's a right triangle. That's Pythagorean theorem. But what if the square of the longest side is bigger than the sum of the squares of the other two sides? Then it will be an obtuse triangle. And what if the square of the longest side is smaller than the sum of the squares of the other two sides? Then it will be an acute triangle. All right, recall, there are two things to discuss when we give you three numbers. First of all, is the triangle even possible? Remember, any two sides together must add up to a sum bigger than the third side. So check all combinations of two sides, 4 and 12, 4 and 9, and 12 and 9, and show that any two sides together are bigger than the missing side. And it is true, so a triangle is possible with the numbers 4, 12, and 9. Next, take the longest side and square it and compare it to the sum of the squares of the other sides. Since the longest side squared is bigger than the sum of the squares of the other two, it's obtuse. And number 2, a lot of students will go straight to the 22 squared and comparing it to 11 squared and 9 squared, but that would be a waste of time because first, don't forget, check, is the triangle possible? And 11 plus 9 is only 20. That's not bigger than 22. So we'd say no triangle possible because 11 plus 9 is 20, and that's not bigger than 22. We got 6. Whoa, what just happened? All right, in this example, we're supposed to find x. And we're given 3 congruent segments, a side of 18 and 30. Well, how are we going to find x? We'll use this yellow triangle, which is a right triangle. We know it's a right triangle because this segment is perpendicular to the bottom segment, which means it meets at right angles. So we've got our right triangle here on the left. And we can use the Pythagorean theorem and say the square of the longest side, the hypotenuse, will equal the sum of the squares of the shortest sides, which are 18, and we don't know here. Let's call this one x. All right, so 30 squared, 18 squared, and x squared. Subtract 324 from both sides. Take the square root of both sides. And x is 24. So if this leg of the yellow right triangle is 24, then since these segments are congruent, they must be 12 and 12, which makes this 12. And now we can find x using this right triangle. Hypotenuse squared is equal to the sum of the squares of the other two sides, which is 12 and 18. Hypotenuse squared is 144 plus 324. So x is the square root of 468. Let's take this opportunity to write 468 in simple radical form. It's even, so 2 goes in there 234 times. 234 is even, so 2 goes into there 117 times. 3 goes into there because 7 plus 1 is 9. And since 3 divides into 9, 3 divides into 117. So 3 goes in, let's see, 39 times. And 39 is 3 times 13. So 468 is 2 times 2 times 3 times 3 times 13. So the square root of 48 is the square root of all that, which means the square root of 2 squared times the square root of 3 squared times the square root of 13. And the square root of 2 squared is 2, and the square root of 3 squared is 3, and the square root of 13 is done. It's in simple form. So our final answer, if we write x in simple radical form, is 2 times 3, which is 6, times the square root of 13. And that concluded what we covered the last day before winter break, section 5.7. I hope this helped.